Okay, welcome to lecture here. We are rolling on, I think, to the next chapter. Should be chapter 21, transition metals, some coordination compounds, complex ions, all that good stuff. All right, so in this chapter here, we're going to talk about, as it says there, transition metals and coordination compounds. So the first part, we're just going to kind of review some of the properties, if you will, some of the characteristics of transition metals. Some of this at the beginning probably be pretty review for you. Talk about electron configuration, of transition metals and so forth. That will then rolls into really a conversation about complex ions, which are a lot of times made up of a transition metal that has a number of ligands attached to it and coordination compounds. And towards the end of this chapter, we will talk about sort of the idea of where electrons sort of go in elements in a complex ion in terms of how they're sort of split up. Depending on sort of the ligands that are attached, the complex ion is there. We also will talk about in this chapter everybody's favorite thing, which is nomenclature, which, you might have thought you were all done talking about how to name things. So we're going to learn how to name all these sort of complex ions, and they can be very long, these names. You might need the whole screen here on some of them. All right, so it looks like most everybody's rolling in here. So let us start then again with just sort of an idea of our transition metals. I would hope, obviously, you know where the transition metals are located on the periodic table. But again, as we will see, and just a reminder, right, the transition metals there are right there between group 2 and group 3 on the periodic table. Or transition metals. As you're probably familiar with, transition metals, one of the main sort of aspects of them that you came across probably was when you talked about sort of regular nomenclature. Those transition metals, again, are the ones that have the ability to make multiple types of positive charges. So since they're metals, they will make positive charges, and they have a sort of what is sometimes referred to as a variable type charge. So depending on the situation, depending on who it is bound to, it may have one sort of charge versus another. So for example, copper can be sometimes copper 1, could be copper 2. Iron as well there, right? Could be like plus 2 or plus 3, depending on the situation. Now, one sort of thing that affects sort of charges and how things get charges, things that lose electrons, what electrons are sort of lost, is an idea was sometimes referred to as effective nuclear charge, or sometimes referred to as Z effective. And the idea behind this is probably something that you learned as well in maybe 1A, is the idea was sometimes referred to as shielding. So the basic sort of idea of that is, for example, let's say we had a nucleus, I'll draw it here, that had a positive 3 charge from its protons. And in that case, maybe it's got a couple of electrons here, another electron out a little further away from the nucleus. And the idea here is when we think of something like this, for example, lithium is what we're talking about, right? 1s2, 2s1. When we look at something like lithium, it has this over here, this one electron, which is its valence electrons, the outermost, and these are what are sometimes referred to as core electrons, right? And as you're familiar with, it is the valence electrons, right, which are the ones that are involved in bonding. And the reason for that, or part of the reason for that, is a little bit about the effective nuclear charge. So these electrons here, for example, they are closer to the nucleus. They're in a lower energy level. They pretty much feel that full brunt of that positive 3 charge. And remember that, sort of as the charges get larger, the numbers, the strength of the attraction also gets sort of stronger as well. So something with a +2, -2 attraction is stronger than a +1, -1 sort of attraction. So those electrons which are closest there, which would be representing those core electrons, they really do feel sort of the full brunt of that positive charge. And they're going to be held obviously a lot tighter because of that. Now, when we think about our valence electron out here, he is what is sometimes referred to as being shielded by those electrons in the lower energy levels. So, you know, for example, instead of that electron on the outside there feeling the full brunt of that +3 charge, perhaps he's only feeling like an attraction of +1, which obviously is not as strong as those guys closer in. And he's obviously then not going to be held as tightly as those guys that are closer in. And that's why, for example, those valence electrons are the ones that are involved in bonding. They're not held as tightly. They're on the outside. They come in contact with each other. So one way you could sort of calculate, for example, the Z effective, which is sort of the effective nuclear charge that that particular electron, say, here would feel, is you would take that positive charge from the nucleus. You would then subtract it from the electrons that are shielding, in this case 2. And again, that guy on the outside is effectively only feeling like a +1 attraction to that nucleus. And like I mentioned just a second ago, that obviously is going to mean it's not going to be held as tightly, going to be easier to remove. And again, why we see some of the trends that we see in terms of sort of transition metals. So if we look at sort of sodium, magnesium, aluminum, that's going across a period on the periodic table, we do see that the effective nuclear charge does increase. And if that means, right, if we're going, one thing that you should be familiar with, right, is if you're heading this way on the periodic table, it is much harder to remove an electron, for example. So we see an increase in the effective nuclear charge as we go to the right, which means even those outer electrons are still feeling a pretty good jolt of positive attraction from the nucleus and going to be held tighter than guys to the left of the periodic table, like where sodium is, for example. That also means that that larger positive charge, right? So as you go to the right on the periodic table, you're also doing that buildup of positive charge, right? Protons get larger as you go to the right. So you have that bigger positive charge in the nucleus going to bring everybody in tighter because it's going to be held a lot tighter. So even those further electrons will be brought in a little closer. And we also see the trend that we also see as we go to the right on the periodic table here. The radius gets smaller, right? And that's because of that positive charge bringing everybody in. And that's what we see here on this diagram. Again, in terms of general sort of trend, we do see that the Z effective increases to the right within a period. And because of that, again, that bigger positive charge, even for those outside electrons, are going to bring everybody in tighter and smaller, and that goes with the same sort of size pattern we see on the periodic table. Size decreases overall, right, as we go this way, and increases as we go this way. And again, that ties really nicely with sort of the effective nuclear charge. There's our transition metals here. Again, between group number 2 and group number 3 are transition metals. These guys, as well, as you may remember, technically speaking, these guys down here, which are usually on the bottom of a periodic table, technically go right in there. And that is technically where these two periods would technically go. And that's why those guys on the bottom are sometimes also referred to as intertransition metals, because they really should go in that sort of area. You may also remember for sort of electron configuration, our transition metals are our D blocks. Yeah, so this is our D block here in terms of electron configuration. And remember that the Ds are 1 behind the period number, so that is the 4th period there. But this guy right here is 3D, right? 4D, 5D, and 6D, which means this guy here technically would be on period number 6. These two down here are F blocks in terms of electron configuration. And the top guy would be 4F, bottom guy would be 5F. Yeah. So for the most part, when we're dealing with transition metals, which we'll deal with a little bit later on as well, when we're talking about sort of complex ions, it is those d electrons that we are essentially going to be dealing with and seeing what sort of happens with those electrons. So transition metals, like anything else sort of on the periodic table, does show very similar sort of properties within a group, or also within a period as well. A lot of those guys do have very similar sort of properties. Now, a complex ion is sometimes formed a lot of times as a result of a transition metal being involved. So a lot of times a transition metal with a relatively high sort of positive charge can form these complex ions. And that also is because, again, these transition metals can have more than one oxidation state. So, for example, something like Mn has a ton of different oxidation states, anywhere from minuses to pluses. And oftentimes those cations are involved in those complex ion formations. They get surrounded by a number of Lewis bases. So if you remember when we're talking about acid and bases, a Lewis base, remember Lewis involving electrons, and that's going to be your electron donor. So remember, a Lewis base is something that will donate a pair of electrons. A Lewis acid is something that's sort of deficient in electrons and will accept a pair of electrons. So a lot of Lewis bases are what are referred to as ligands. And again, they have a pair of electrons that they're able to donate in. So if we look at something like this, which we'll also see a little bit later as well, this is an example of a complex ion. We have our transition metal in the middle. We have 1, 2, 3, 4, 5, and 6 ligands attached. The NH3 here would be our Lewis base. Again, if you just quickly sketch NH3, it is a polar molecule with those non-bonding electron pair that it can basically donate to our cobalt, which is electron deficient. Otherwise, it wouldn't be a positive charge, so it's deficient in electrons. And since NH3 is neutral, the overall guy there is +3, this complex ion. And by the end of this chapter, you will know how to properly name that guy, something like hexamine cobalt 3 ion, something like that. You'll be able to give the proper name to something of that nature. So ionic compounds are a lot of times, they will produce these sort of colored solutions. Some can be blue, some can be pink, for example. It can be some other colors as well. And it does have to do a lot with sort of the color of light that it absorbs, or the wavelength of light that it absorbs. Remember that when we see a color, to us it appears one color, but in terms of the wavelength of light that it's absorbing, it's actually sort of the complementary color to that. So for example, if we saw a solution that was red, and we wanted to do the absorbance of that sort of value using like a spec 20 or spectrophotometry type of equipment, we wouldn't set the wavelength to red because that's not really where it's absorbing. It would be absorbing in a different wavelength complementary to red, would be where you would kind of set the wavelength to. Many ionic compounds as well are paramagnetic. So paramagnetic, as you may remember, is like unpaired electrons. Yes. You know, so remember in a orbital, right, you could have electrons that basically can put 2 electrons in an orbital represented by an arrow, one having a spin quantum number of +0.5, right? One having a spin quantum number of -0.5. And again, when they're in the orbital in this direction, this is what is referred to as being paired spins. And when we just have sort of one electron in there. And that's how they go into, say, like p orbitals, right? They go in one at a time and then come back and pair. Something like this would be paramagnetic. Again, unpaired electrons is sort of what we're looking at. Paired off electrons not involved in paramagnetic. We'll talk a little bit about electron configuration. A couple of things that you probably are familiar with as well is, again, they do get into the d electrons. So following that 1s2, 2s2, 2p6, 3s2, you know, you could do the electron configuration such as that. So for example, again, something like iron, which is 26. And again, you probably learned that kind of zigzag move there for electron configuration. And if you write it out, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, if I got that right. So that is 10, 20, 26. This is what is sometimes referred to as noble gas configuration, right? So if we take up to here, that is counting the top there, 2, 4, 10, 12, 18 electrons. 18 electrons on the periodic table is argon, right? So we could do sort of noble gas configuration. That means argon's configuration, and 3d6 would be continuing on. So you could write electron configuration either way, sort of a shorthand, if you will. And what we see here is, I think I missed some there. 4s2 should still be there. Sorry, that's a bad counting. That's 10 and 18 is actually right there. Let's get a calculator and try that again. There we go. So this guy would be out with this guy. There we go, 4s2. Let's try that again. Argon, 4s2, 3d6. There we go. We'll grab the calculator next time. All right. Now, there are some exceptions sort of to the normal electron configuration when we talk about transition metals. And those normal exceptions, two very common ones that people think about are chromium and copper. And chromium and copper basically have one more electron in the d orbital and one less electron in the s orbital. So chromium, which is 24, and copper, which is 29. So again, normally if you just sort of wrote it out there and you followed the normal electron configuration, you would do something such as this, and then 3d4. So experimentally, it's been found to be more stable with that extra electron sort of up into the d orbital, and you do end up getting that transition. You also get a similar type of exception that occurs for copper as well. So in the case of chromium, you're kind of filling in an electron going parallel there in each of the d orbitals, while in copper, you're kind of filling up all the d orbitals there, pairing everybody off. This can happen because when the electrons go in, they do go into the 4s first, right? Followed by the 3d, for example. They're very, very close in energy. And as you may be aware of as well, and we'll talk about in just a second, as soon as you actually start filling those orbitals with the d electrons, there's actually a switch that occurs. And you actually end up with the 4s electrons higher in energy than you do the 3d. And that's important for, as we'll talk about in just a second, what happens when they do form ions. And because there's that switch that occurs, the 4s's actually end up being higher in energy than the 3ds, and that's important for which electrons get lost first. This is also, if you look on the periodic table, where copper and chromium is, and kind of underneath those guys, like silver and some other guys, you will see very similar sort of exceptions. There's a lot of these kind of exceptions that occur in that area of the periodic table. And again, just because those orbitals are very close to each other, or those subshells are very close to each other, it doesn't take a lot for electrons to kind of transition up and down in that sense when when that happens. There's even some transition metals, if you look at the correct electron configuration, have been found to occur with no electrons in the s orbital. Yeah, so they're actually not the only exceptions. Again, you know, if you look on the periodic table, underneath those guys, actually right underneath those guys, is where a lot of those exceptions occur. Actually, if you go periodic table underneath chromium copper and then kind of together underneath in that transition metal region, if you look at the electron configuration again, you'll find a lot of sort of exceptions to it where those occur. So in most classes, most people just focus in on chromium and copper because it's the first row. And, you know, for us to, you know, those are probably the only two exceptions you should worry about, but you should be aware there's definitely more than just those two in there. Now, when we do talk about electrons and ions being formed from these transition metals, because there is that sort of transition that occurs when you start to fill those d orbitals with electrons, that the 4s actually becomes higher in energy than those 3d, for example. When we go to make ions or cations, it's always these s electrons that gets lost first. So we lose these s electrons first when we form ions involving transition metals. And then if you need, you can then kind of dip into the d orbitals at that point to get the right electron configuration. And so, for example, here, if we look at Ti, and then we get Ti with a +3 charge, even though in our electron configuration, as we could see, is written like this, because there is that switch that occurs, we will lose the first 2 electrons out of the s, and then we will have to dig into the d at that point for the 3rd electron, and we will end up with an electron configuration as argon 3d1, if you didn't write it all out. Same thing with our iron, for example, our iron there, which is 26, as we saw. And if we had iron with a +2 charge, that means it would have 24 electrons, which means its configuration would be, we'll start here again with that one, argon 4s2 3d6, which would be iron's configuration. Now, when it becomes +2, it is going to lose these 2 electrons first, and the configuration would be argon 3d6. If we got to iron with a +3 charge, that means it would have 23 electrons. Same idea, we would lose those first 2 electrons from the s, and now we would have to come into here, and we would end up with argon 3d5. So transition metals are a little bit different than representative elements. Typically in representative elements, we take out the last electrons in the electron configuration when they lose ions, but transition metals always will lose the s's first and then go into d's. And that happens for the 2nd row, 3rd row, and so forth. In terms of those transition metals, they will lose those s's and then go into there. This is also why sometimes you will see, for example, sometimes people write electron configuration like this, where everybody's in order, like all the 3s are together, all the 4s are together, and maybe you've seen that. And that is sometimes written based on energy, not filling, because in reality, once you put those d electrons, the s's actually become higher. Probably 9 times out of 10, most people in chemistry classes don't write electron configuration in terms of energy, but they do it in terms of what is referred to as the filling order. And in the filling order, basically, it is what we normally expect it to be, 4s first, for example, and then 3d. So you should always probably write your electron configuration in this order here. Again, filling rather than energy. But sometimes if you search around, like on the internet and stuff like that, you'll actually see people sort of write everything in terms of, it almost looks like in order. All the 3s are sort of together, you know, all the 4s are together. And that's usually written, if it's done correctly, it's usually written because of energy rather than filling order. But again, in most chemistry classes, it is the filling order that you typically do write the electron configuration, and how you should write it in this class as well. So why don't you take a second just to make sure, nickel with a +4 charge. In case you don't have a periodic table, nickel is 28 on the periodic table. Okay, so 28, and again, if we just sort of wrote nickel with no charge, we'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8. Nickel with a +4 charge would mean it lost 4 electrons, which means the nickel would be down to 24. Again, here what's going to happen is we are going to lose these 2 electrons here first, and then we need to take the other 2 out of there, and we would end up with 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 in this case, are argon 3d6 in that particular case, as right about there is argon's configuration. Any questions on that there? Now, to answer a sort of question I was asked earlier, again, just for example, you know, if you look at MO on the periodic table, its configuration would be krypton 5s1, 3d5. So again, you see 1 less electron, the S, 1 more. If you look at something like PD, it ends up being krypton 5s0 and 4d10. Actually, both of those S electrons have sort of been promoted up there. And again, if you look sort of in that area on the periodic table, right where chromium and copper is, and down and kind of into the middle between the two, there's a lot of these sort of exceptions that you come across. But again, for us, we'll stick with the normal one that most people has to remember, which is, again, the chromium and copper, the 2 exceptions. Any questions on what happens with electron configuration? All right, so let me see here. Let's grab something here. All right, so let's continue then looking at some other sort of, I guess, trends, some information about transition metals. You wouldn't necessarily have to include the 5s0. I just did this to show you that they lost those 2. Most people probably write that one krypton just for D10 at that point. Not necessarily wrong if you did write it with the 0, but most people probably would leave it off. All right, so let's talk a little bit about some of these, at least the first row transition metals and sort of what's happening. We have our oxidation states that we talked about. So obviously we talked about oxidation states, oxidation numbers. And for the most part, this is, again, the first row transition metals heading from number 21 there to zinc, which is 30, and heading in that sort of direction. And what we see is you see sort of a rise in terms of oxidation numbers as you get to sort of the middle there where Mn is, and then it sort of drops back down and all that good stuff. You also see that for the most part, most of the common ones here are kind of the reddish color, a lot of +2s and +3s that we're very familiar with. But you can see something like Mn, for example, can have a ton of different oxidation states, again, depending on sort of what it is hooked to or hooked up to. But for the vast majority, we do see probably +2s, +3 is very common. And you can see definitely as you go to the right-hand side there, more common is sort of the lower oxidation state. Again, for that sort of general trend, right, as you go to the right on the periodic table, you know, things tend to hold on to their electrons a little bit more. So they sort of have a little bit lower oxidation states than kind of further to the left there in that row, where things on the left typically will sort of give away electrons a little bit easier. One sort of important effect on whether or not or why things sort of give away electrons or gain or lose electrons is the idea of ionization energy. And ionization energy, right, is the energy that's required to remove an electron from the gas phase of an atom. So the ionization energy, you could sort of think about it when we remove an electron. Obviously, that is something that then is going to become positively charged, or a cation. So a lot of times we think about ionization energy in association with cations being made. And electrons come off, as you may know or may not know, electrons come off basically one at a time. So for example, if we were talking about sort of the iron, right, the first thing that would happen is the iron would drop that first electron, and the energy associated with that process would be ionization energy number 1, or the first ionization energy. Then this guy would then drop off another electron, and this would be the second ionization energy. Same thing happens with, say, something like magnesium. Again, going to drop that first electron, and then this guy would drop that second electron off. So when somebody says first ionization energy, second ionization energy, third ionization energy, again, that's basically the energy required to remove one electron at a time. As you may also guess, it is probably easier to remove the first electron than the second. When you remove an electron, right, you lose some of that electron cloud, everybody shrinks and gets smaller, which now means your outer electrons are even closer away and closer to your nucleus than they were before, because you have bigger positive charge than negative charge from your electrons, going to bring everybody in. And it makes it harder to remove the second one, obviously harder to remove the third one. And that is typically what we see if we look at the differences between ionization energy 1, 2, 3, and all the way down. For example, sodium here is 495 to drop that first electron. Then we're at 4,500 to drop that second one, so a major jump. We'll talk why that is in just a second. Magnesium, 735 for the first one. It doubles almost for the second electron, and then it gets very big for that third electron. So the general pattern that we see in terms of ionization energy is the first ionization energy is usually smaller. Second ionization energy is usually larger as well. We also see just in general on the periodic table, which you may be familiar with, is the general trend in ionization energy is it increases as you go to the right and up and decreases as you go down. And that also makes sense if you think about what's to the up and right on the periodic table. Those are nonmetals, which typically don't give away electrons. So it takes a lot of energy to try to remove those. While if you go left and down on the periodic table, you have your metals, which typically will give up electrons pretty easily. So you don't have to put a lot of energy in there to do that. So we do see sort of a big jump in terms of ionization energy, for example, especially when we look at something like sodium here. So, you know, that first one where we would see that first electron come off, you know, it's whatever it was there, 495. Now our second one where this guy would drop off another electron, become Na2 plus and an electron, is a now 4,560. And you may remember when we talk about sodium, it normally makes a +1 charge always. And the reason for that is if we look at the electron configuration for something like sodium, 1s2, 2s2, 2p6, 3s1, when it loses that first electron, that is its valence electron, right? So not a ton of energy needed. But now when we get down into, if you wanted to remove that second electron, you're now into those core electrons, right? And those are the ones that are closer to the nucleus, going to be held way tighter because they are closer to that nucleus. Takes a tremendous amount of energy to do that. As you can see, again, almost tenfold more amount of energy to remove that electron, and typically doesn't happen, right? So that's why we say sodium will always make a +1 charge, because it has that one valence electron, which can, I'll just say, easily be removed in comparison to once you start trying to dip into those core electrons, they're just way too close to that nucleus, feeling that full brunt of that positive charge. You almost got to get in there and try to rip it apart, which under normal circumstances doesn't really happen, obviously. And that's why we see sodium will have a +1 charge. That's why we also see the big jump here with magnesium as we go from the second electron to the third, because once you go to that third electron for something like magnesium, you've now dealt into its core electrons. And aluminum, you see the same trend. Aluminum can go +3. First electron, 580, 18, 15, and 27. But as you go from that third electron into those core electrons, that's a huge jump in terms of energy to try to do that. It's like 11,000. You're going from 2,700 to 11,000. A tremendous amount of energy that usually doesn't occur in that particular case. So, you know, ionization energy is that energy that we associate sort of with the formation of a cation. And again, much easier to remove those valence electrons because they're further away from the nucleus. They have a smaller effective nuclear charge. They're not being held as tightly. But again, as you sort of move in towards those core electrons, it gets much, much harder to try to remove those. Here's a whole bunch of information, which obviously you should memorize. I'm kidding. Don't memorize it. But with some of this stuff we talked about, I'm not sure how much you can see it on your end, but we'll just generally talk about. In terms of electron configuration, we talked about it in general size, right? As you go left to right on the periodic table, things get smaller. So that's the general trend that we see. Ionization energy, which is in electron volts in this particular table, we do see the same sort of pattern. As we go to the right on the periodic table, ionization energy increases. And as we go from the first ionization energy to the second to the third, the energy required to remove each of those electrons one at a time, it also increases. Common oxidation states, as we talked about there, +2, +3s. Density, we see a slight increase as we go to the right there in terms of density. Again, the volume can get larger, a lot more electrons, so the density will... the mass gets larger and the volume gets sort of smaller in terms of that as everything gets squished together and the density goes up in that case. Here's a graph of showing that again, first ionization energy versus third, and you can see a tremendous sort of increase in it as you go from the first to the second to the third. Second would be in there, which I think is the next slide. In case you didn't like that first one, here's all three of them together. But again, you can see that pattern. And in general, as you go to the right, again, increasing in that ionization energy. Another sort of trend which is important for transition metals is what's known as electron affinity. And electron affinity is different than electronegativity, which you may be thinking. Electronegativity is the ability of an atom to bring electrons towards itself. That's what you talked about when you talked about bonding and bond dipole, the difference in electronegativity values. Electron affinity is, I won't say the same, but it's a similar sort of idea, I guess. Electron affinity means if you have an affinity for something, you sort of like it. And if you like electrons, that means you want to bring electrons and gain electrons. So when we think about ionization energy, we think about it in terms of the formation of cations or positively charged ions. When we think about electron affinity, we think about it in terms of gaining electrons, which would mean anions. So we sort of think about electron affinity as the sort of thing that helps us understand anions when they're formed, which are negatively charged. And it's really that energy difference that occurs when an atom is able to gain an electron in its gas phase. So one thing that you may remember is, for example, sometimes when we think about something like sodium chloride, which is solid, and we dissolve it in water, we sometimes think about that process as sort of a one-step process where it just goes this way. And perhaps you may remember from 1A, if you talked about it, that there's actually a step that occurs before that where these guys become ions in the gas phase. Yeah. And then they basically get hydrated with the water. And that is what's sometimes referred to as like the lattice energy, right? The energy needed to kind of break those guys apart into their ions and then get hydrated, and you add up all that energy, and that's the overall thing that we sort of think about. So sometimes we think about it sort of happening all at once, sort of maybe does happen very quickly, but it's actually a two-step process that occurs when we sort of hydrate those ions from the solid state to its aqueous state. And so when we talk about electron affinity, it has to do with really the energy change that occurs when an atom basically gains an electron. And for the most part, the general trend is, and it's not perfect, but the general trend in terms of electron affinity is it increases as you go this way on the periodic table and decreases as you go down. It does very much follow sort of the electronegativity trend, which also increases to the right and decreases down. But it's sort of that energy change that occurs. Sort of the more negative it is, the more chance it's going to gain an electron. And this, for example, is group 7. And for the most part, if we go up group 7, we do see an increase in the electron affinity. And as I said here in this group 7 is actually a very good example that it's not perfect. So you can see that the energy change between, say, fluorine and chlorine, chlorine is actually more than fluorine. So again, not perfect in terms of the trend, but that is sort of the general trend that happens with electron affinity, increases up to the right and decreases left and down. And again, so ionization energy we think about in terms of cation formation. When we talk about sort of anions being formed, we talk about electron affinity, which is that energy change that occurs. Any questions on that there? Here's another table with some other sort of properties similar to what we were talking about. This is a table of relative reducing ability of our first row transition metals. And reducing ability here is increasing as we go up this table. And just for orientation purposes, this is going, I'll go this way, I guess I'll write it this way. This is left to right on the periodic table. So that's your first row transition metals going left to right, starting up here, if you look at your periodic table. And what we see is the reducing ability sort of increases as that way. And that means that up here, we have something that is going to be oxidized, something is going to be reduced down here more often. And you may say this is like our potential voltage, but isn't the one that's more positive going to be our cathode and be reduced? And you are right, but the important part of this is if you look at these equations, These are not standard reduction potentials. These are all oxidation reactions. Yeah. The electrons are on the product side. And so you would think up here would be the one that most likely would be reduced. But in this case, if we reverse this reaction and we looked at SRP values here, this guy would become negative, 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 negative. All these guys would be negative. And actually our one guy that's positive would be, or negative would be our positive guy if we looked at SRP values. That means that the guy on the bottom there, right, would be most likely to be our cathode and be reduced. Top guy would be our oxidized guy and be our anode. So again, these are not SRP reactions like we've been looking at. These are actually standard oxidation potentials, which are really nice oxidation reactions. So that's why reducing ability, or being a reducing agent, increases as you go up, because those are things that are most likely to be oxidized. So again, this is sort of opposite of what we were talking about, or how we've seen it, I guess is a better way of wording that, how we saw it in the previous chapter. Any questions on that there? All right. Here's our atomic radii. So as we talked about, again, heading to the right, we see a decrease in our first row, second row, and third row transition metals overall. And we also see a increase in overall size as you go down on the periodic table, right? So overall size as we're going this way, and that's going down on the periodic table, again, getting a little bit larger to start with, but the general trend is decreasing as you're going to the right. Here's what all those guys look like, just in case you need to see them somewhere. I'm not sure. These are a whole bunch of stuff that, you don't have to worry about, because, you're not necessarily doing the general unknown in person, but it's sometimes helpful. All right, any questions on transition metals? So in general, what you need to know is obviously where they are, I suppose. You need to know some properties of the transition metals like we talked about. You know how to write electron configuration for them, for both those guys and ions that are present. And I think, that's about it for transition metals. Again, hopefully most of that was review. That should hopefully be some stuff that you talked about, I would hope, in 1A. All right, then let's get to sort of the heart of this chapter, which is coordination compounds. And coordination compounds, sort of for a lack of a better word, is sort of an ionic compound. And it basically has a positive guy and a negative guy when you have a coordination compound. And as we talked about, we have one that's a complex ion as part of it, and we have a counter ion. So the complex ion can be positive or negative, just like our counter ion would be positive or negative. So if you have a complex ion that is positive, your counter ion will be negative to balance out the charge. And if you have a complex ion that's negative, your counter ion will be positive to counterbalance the charge. So really, it's sort of just like a traditional ionic compound, like we talked about, or you talked about when you did regular nomenclature. Whenever you put something that's positive and something that's negative together to make a coordination compound, it should equal 0 overall with the charge. And that's the same idea here. A complex ion, as we've sort of talked about a little bit before, and we'll talk a little bit more detail here, a complex ion is basically, again, a small metal that has a positive charge. And again, it is bonded to one or more molecules or ions. And those guys are what are referred to as ligands. So these ligands, again, are Lewis bases, which, as we talked about just a second ago, are guys that basically have something like a pair of electrons that they could donate. So a ligand needs at least one unshared electron, usually in sort of a polar molecule is really good for it. So water, which is polar, right? It's got its non-bonding electrons here. NH3, which is also a polar molecule, also has its electrons that it could donate. Obviously, something that has a negative charge means that it gains some electrons, so it's got some extra electrons to donate. This is something like carbon monoxide as well. a polar molecule, right? Heading in that direction, this being more negative, this being more positive, has those pair of electrons that it can donate. So our complex ion, again, will have those ligands that are attached to it, and our coordination compound is basically a neutral compound that's made up of both a complex ion and a counter ion. And again, the goal there is to get to sort of zero for the overall charge. So something that we touched upon, I think, in an earlier chapter is an idea that is known as basically coordination number. So when we talk about the coordination number of a complex ion, it is basically how many donor atoms or atoms that are directly attached to the metal in the complex ion. So for example, if we go back and look at this guy here. So to this cobalt, which is our metal, directly attached to it in terms of atoms is we have one Cl atom attached to it, two Cl atoms. In terms of our NH3, as we can see here, it is just the nitrogen that's actually attached. So we have the nitrogen, that guy attached, nitrogen, that guy attached, nitrogen, that guy attached, and the nitrogen in that guy attached. That is 1, 2, 3, 4, 5, 6. The coordination number here would be 6 for this complex ion, as it has 6 atoms that are directly attached to the metal in this complex ion. Now, it's important when you think about the ligands that are attached, what type of ligand it is. Now, in the case of water and in the case of NH3, these are both what are referred to as being monodentate. Which basically means for every one of those molecules, it will attach in one place. So for every water molecule, it's only going to attach to the metal via the oxygen. The nitrogen here is only going to attach to the metal via the nitrogen there. Now, there are some ligands that actually attach in multiple places per molecule. A very common one is this guy here, which is ethyl endyl diamine. And it is sometimes abbreviated with an EN and just some parentheses around it, because people don't want to write out ethyl endyl diamine. So they'll use that abbreviation a lot in coordination compounds. So if you see that EN, it basically means that. And basically, if you draw it here, you know, it looks something maybe like this. And for every one of these EN molecules, if you have a metal, this nitrogen on one side will bind to it, and the nitrogen on the other side will also bind to it as well. And for every one of those particular ligands, you get like a 2-for-1 deal, which means if I had 2 of them, draw one this way since I don't have a lot of room. This guy would attach, and this guy would attach. And if I had, I'm just going to borrow this guy on the bottom here. This guy would attach, and this guy would attach. Now, if we look at this metal and ignore this metal down here, we'll get rid of it. It has attached 1, 2, 3, and 4 places. So the coordination number in this guy would be 4 in this case, even though we only have basically 2 of those ligands attached. But each of the 2 ligands can attach in 2 spots per molecule. So for every one, you get 2 in terms of the coordination number, and the coordination number will be 4. It's important to remember that, because sometimes people, when they see formulas for complex ions, you may see the formula like this, where it's like metal En2, and they'll go, oh, the coordination number is 2 because it says 2 there, so that makes sense, right? But again, because this is bidentate, it could actually bind 2 for 1, so the coordination number is 4 in that case. So ethylenediamine EN is a very common one. Another common one is everybody's favorite oxalate. So if you draw oxalate really quick, give it the old college try here. Looks something like this. This oxygen at one end, the single bonded oxygen at the other end. For every one of those oxalate molecules, both of those oxygens could actually bind into the metal and bind to it. So again, you get a sort of 2 for 1 situation that occurs. There are some that could do 3 or more. They're sometimes referred to as being polydentate, EDTA, ethyl-diamine tetraacetic acid. We'll see it in a second, I think, on another slide, but it could do something like 6 places per molecule. So for every EDTA, it's a really good thing. It could grab metals really good. Every one of those will grab a metal in 6 different locations and kind of tie it up, as we will talk about in just a second. So you may ask yourself, well, how do I know sort of how many ligands I'm going to get? You know, how many are going to surround? And there is sort of a general pattern that sort of occurs. Again, nothing unfortunately is 100%, but guys with +1 charges, like you see there on the left, typically will make coordination numbers of 2 and occasionally 4, as you can see. Guys with +2s typically do 4 and 6, and ones with +3s typically will take in 6 guys, except for gold, which typically will do 4. So some common sort of patterns that you see with these guys in terms of their charges, sort of as you can see, as you increase the charge on there, you can kind of handle a little bit more in terms of ligands coming in and attaching. Kind of the smaller the charge, a little less in terms of that. And here's, I guess I drew it not too bad, my ethylenediamine, which can do that in 2 places under those nitrogens. And this is EDTA over here, and EDTA and something like this, which are sometimes referred to as chelating agents. They're really good at grabbing up metals. And this structure here, besides the lead, everything else besides the lead here is EDTA. So it could attach 1 place there, 2, 3, 4, 5, and 6. So in one EDTA molecule, you can basically attach 6 places around a metal. And that's why a lot of times EDTA is used as a metal chelator. So if you look at actually like ingredients on certain things like shampoo and those type of things, you'll oftentimes see something EDTA is sort of in there. And a lot of times it's used to sort of gobble up or sort of take out metals and stuff like that. Because it does a really good job. It basically surrounds it, it grabs it, and pretty much that metal is not going to go anywhere. And if you needed to, you can basically kind of get rid of it. Here's a table, I believe from your book. It's some common ligands. So we have a lot of our monodentates up here. Some of the ones we talked about are water, cyanide, nitrite, ammonia, hydroxide, thiocyanate, any of the halogens as well. They're typically monodentate. We have our couple of really common bidentate or oxalate, which again, this oxygen and this oxygen can bind to the metal per molecule, and then our EN, which is our nitrogen, and our nitrogen being able to bind into there. This is diene, which has actually 3 ethyl nitrogens, 1 nitrogen there, 2 and 3 has the ability to bind. And here's our ethylenediamine on the bottom there. Again, those 6 locations where we can bind into it. And you can also see, by the way, EDTA, we got 1, 2, 3, 4, maybe like a -4 charge happening with it. And again, at each of those 6 places, it's able to do that and bind in. All right, so why don't you on this one here take a minute or so and figure out what is the oxidation number on the metal in the complex ion part. And while you're at it, why don't you figure out the coordination number for the complex ion? I will give you a hint. typically the thing in the brackets is our complex ion. So see what you come up with, and we'll talk about it in a minute or so here. Okay, so let's take a look at each of these and sort of figure out what's going on. So we'll start with the first one. So as I mentioned before, a lot of times coordination compounds are written like this, where they will put these sort of brackets around the complex ion part. So that's a very good way to sort of figure out, complex ion part, which part it is, and which part maybe is the counter ion. So what we got going on in this particular case is this part here is our complex ion. And the K here would actually be our counter ion in this particular case. So when we're talking about the oxidation state, we're looking at the gold here. And we have hydroxide here, which is -1 each. And there's 4 of them, which gives us a -4. The potassium is +1. So +1 and -4 means that the gold here should be +3 in terms of its oxidation state. So the gold would be +3. And when we look at the coordination number in this case, the coordination number for this guy would be 4. Hydroxide OH minus is a monodentate ligand, so it will attach one place per hydroxide. And there's 4 of them that are attached to our gold. Now, when we take just the complex ion part by itself here, as we just figured out, the gold is +3. The OH minus is -1, so that's -4. So the complex ion part in this particular case has an overall charge of -1. And that is why when we look at our counter ion, which is the potassium, we just have one of them because that will give us K+. +1 and -1, just like you do with a normal ionic compound, will give you 0. And that's why when we put it together, we just need one counter ion with our complex ion to balance it out and give us our overall sort of formula there. In this particular case, our complex ion is an anion. And our counter ion is the cation. And as we'll talk about in just a second, just like normal ionic compounds, it is always positive then negative, right? So cation then anion, so positive then negative guy. And that's exactly how we should look at this guy. Any questions on that first one there? So let's take a look then at the second one. Now the second one here, I'll just take the writing here. There are brackets right here, which means this is our complex ion. And by the way, since it comes first in the formula, we know that it is positively charged. This NO3 is our counter ion here. So let's see what we got going in terms of what's happening. So starting with the NH3, NH3 is neutral, 0, no charge. And that means who cares, there's 6 of them. NO3 is nitrate, which is -1, and there's 3 of them, which means it's -3. That means the chromium in this case is actually +3 in terms of its oxidation number. Now, the coordination number for this guy is it has basically 6 ammonias attached. And as we saw earlier, ammonia is a monodentate, which means the coordination number here would be 6 for the complex ion part. Now, when we look at just the complex ion part, again, if we just pull the complex ion part out, this has 0, this is +3, which means the overall complex ion in this part is +3. Our counter ion is nitrate, which is -1. So to balance it out, we don't need one of those, but we actually need 3 of them, which is why the 3 is right here. So we need 3 of those counter ions to balance it out. And this is actually opposite of what we had previous. Our complex ion in this part is our cation. And the NO3 minus is our anion, our counter ion. So these two here are a pretty good representation that both the complex ion could be either positive or negative, as we see, one of each case. And then obviously our counter ion could be either positive or negative. And again, the idea here is just like basic ionic compounds. We want all the positives and all the negatives to balance each other out when we make a coordination compound. So it should be a nicely balanced, no overall charge when we're dealing with a coordination compound. Any questions on that there? All right, so let's then talk about how we go about naming these things. So we're going to talk about some nomenclature here and how we go about naming them. And there's a whole bunch of rules which, you know, are wonderful. Sarcastically saying that. So let's talk about what's going on here with our naming. So the question was, before we get there, the OH is -1 because hydroxide is hydroxide in general is -1 to begin with, right? Overall, hydroxide has a -1 charge, and that's because hydrogen here is +1, right? And oxygen is -2. So -2 and +1 gives you -1 overall in terms of oxidation number. Remember that if you do have a charge, for example, on a polyatomic ion, like we have on nitrate as well, you might as well just use the overall charge of it, because the overall charge of it is pretty much all the oxidation numbers together. So when we look at something like nitrate, which is NO3 minus, it really is, this is -2, and this is +5 in this case. And that's how we get to the -1 overall. So by taking the overall charge when you're dealing with something that's a polyatomic ion, it basically already did all the math for you in terms of the individual oxidation numbers. And that's, that allows you to kind of quickly figure it out in terms of their charge. You could definitely go individual, but it's a lot quicker to kind of, since it's already there for you and kind of does the math for you, might as well take that overall charge. So let's talk about the rules for naming these guys. So as I mentioned before, the cation is always named before the anion. So we always both, just like a normal ionic compound, the positive guy before the negative, both in the formula and also the name as well. So that is how it normally will go. So always positive, then negative. If you have a complex ion, the ligands are named first in alphabetical order, and the metal is always named last. So what this means is, as we've been talking about, there is basically two parts to these guys. This is made up of, again, that complex ion and also the counter ion. Now, when you're naming the part of the compound that is the complex ion part, you put all the ligands in alphabetical order, regardless of the prefixes, by the way, just alphabetical order. And then the name of the metal should always come at the end of the complex ion name. That does not mean that it will always come at the end of the actual name, but it should come at the end of the complex ion part of the name. And we'll kind of point that out in just a second, but it doesn't, again, mean that you should always end your name with the metal, but you should end the complex ion part of the name with a metal. Now, names of anionic ligands will end with the letter O. Neutral ligands are sometimes called by the name of the molecule. And there are some exceptions, like water is known as aqua. Some books use aqua, A-Q-U-A, instead. So sometimes people will use A for that guy as well. CO is carbonyl, NH3 is amine. When several ligands of a particular kind are present, so if you have more than, say, one ammonia, like we saw in that, or more than one chlorine, you use prefixes like di, which means 2, tri means 3, tetra means 4, penta means 5, hexa means 6, to indicate how many you have. Now, everybody's favorite thing, if the ligand itself already contains one of those prefixes in it, then instead of di, tri, tetra, you would use bis for 2, tris for 3, tetrakis for 4. So what do we mean by that? That we can go back to our friend En, and let's go find that guy real quick. Here he is. Oops, come here. Right here, if you look at En's actual official name, that is ethyl endyl diamine. Yeah. So in the actual name of that ligand, it actually has a Greek prefix in the name built into its official name. So if you had more than one of those ligands present, you would not use, say, di to represent that. You would use something like bis to represent it because it actually has it part of the name. It's kind of a weird one. Oxalate is another one that, although it doesn't necessarily have it in the name, I guess, most people don't visualize it that way, but people commonly will use bis, tris, tetrakis with oxalate as a ligand when it has more than one. So that's another very common one that it is sometimes used for. Now, the oxidation number of the metal is written in Roman numerals. So very much like what you do when you do type 2 nomenclature with those transition metals, you need to include the Roman numeral for the charge on the metal. You do need to do that here as well. Also, something that's kind of different than what you normally would do. So for example, when you have something like, you got something like silver, right? Normally you would just call it silver. You wouldn't use a Roman numeral or anything like that because it has a fixed charge. Typically though, when you're doing coordination compounds, complex ions, you would put the Roman numeral 1 there. And you might even see a Roman numeral. I guess it's really not a Roman numeral, but you could have a neutral metal. As odd as it sounds, things could come together in a neutral aspect, and the metal actually will not have a charge. And you would actually put the Roman numeral, again, not really a Roman numeral, you put 0 in the place of that in there as well. So that's sometimes some things that kind of mess people up because they're like, whoa, like zinc and, you know, silver, they typically don't include Roman numerals on them. But in this sort of nomenclature, we actually do sometimes, or most of the time. Now, the last thing that also messes with people is the idea that if your complex ion part is negative, it's an anion, then you use sort of those old school name, if you will, for the metal. So perhaps when you learned about, hey, iron 2, iron 3, you learn names like perhaps it's ferrate or ferric. Maybe for copper, right? It's a copper 1, copper 2, cuprate, cupric. So if your metal or your complex ion is negative, we use sort of that old school name with the ATE. So iron would become ferrate, copper would become cuprate, and so forth. when we name it. So as an example of that, like we were looking here, our complex ion part here is negative, which means when we go to name this, we would not use gold, we use R8 for gold. While over here, our complex ion is positive, which means when we get to chromium, we would use just regular chromium to name it. So if your complex ion is negative, you got to kind of go old school name. If your complex ion is positive, the metal gets just a regular name off the periodic table like you're used to doing. Any questions on that? So let's look at some tables here of some of these things. Here's a table, I think from your book as well, of some of these ligands and some of the names. These are monodentate, so water you can see is aqua, amine, methylamine, carbonyl, nitrile. Our halogens are sort of named very much like how you name it with organic chemistry. So fluorine is fluoro, chloral, bromo, iodo. Hydroxide becomes hydroxo. Cyanide becomes cyano in terms of the names, how you would use it if you were doing some naming. I think we've got a few more tables. Here again is sort of the older school way of naming some of these metals. So iron becomes ferrate, copper becomes cuprate, plumate, arginate, aurate, stannate. So sort of those older school names. And again, we use this when the complex ion part is negative. So that complex ion part would be negative in that particular case. Here's a few more sort of ligands, again, not from your book, but you have similar ones, I think. So some of our favorite ones, carbonato, right, for carbonate, oxalato for oxalate, feels like you're ordering coffee or something, right? Take an oxalato with a carbonato on it or something like that. Here's our ethyl endyl diamine. And again, on this one, both in the formula and also the name, EN is used a lot. So EN is a weird one. They'll use it both in the formula and also the name for it. And this is our EDTA, which that's a mouthful right there, right? In terms of how you name that guy as well. And I think since we're getting to the end here, was probably a good place to stop. Tomorrow we'll actually get into naming some of these guys and everything like that. The exam will be just like we've been doing it, and it will be the chapters that will be on there. Everything before today, I think, yes. So this electrochemistry should be some thermodynamics, I think. I feel like there might be one more, but maybe not. Just those two, I think, is what's on there. We do have lab today. We are doing experiment number 19. There was no pre-lab or anything like that. There's supposed to be, but never got it up there. So there's no pre-lab. But we are doing experiment 19, just so you know. So that should be corrosion or something like that. And that's what's on tap for lab. It'll be new for me as well. So, hey, we'll do that one. Any questions on that? All right, so we will, I guess, stop here. Make sure you put here if you didn't do so. We'll start lab about 3. And again, we are doing experiment 19, which I think is about corrosion and stuff like that. All right, I'll see everybody in about 10 minutes or so. Get up, stretch, maybe 15 minutes, get up and stretch, and we'll see everybody. Should be experiment 19, corrosion.